All right, let's go ahead and solve problem one. So I think problem one has a typo in it, but it's okay. We're still going to solve it and learn a lot from it. So we have a vapor mixture of acetone and nitromethane. So we're told Y1 equals 0.7, initially at a pressure of 7 bars and 110 degrees C, which is to be liquefied by compression under constant temperature. Right. So how I interpret this is essentially Z1. Right. They label it as Y1 because they're labeling this as a vapor phase, which we're going to liquefy by compression under constant temperature. So it's going to be a vapor phase in which we're going to increase the pressure right until it becomes a liquid. So I'm going to take this to be Z1. I'm guessing they just label it as Y1 because they meant it to be a vapor. Okay, and then we're told it's at 7 bar and 110 degrees C. Then we're asked at what pressure does the system fully become liquid? Calculate the last bubble that condenses, and what is the fugacity of nitromethane in the liquid when the system is at the conditions of part A. Okay, so where I think it's a typo is that we're given saturation pressures at 110 degrees C. This is P1 sat and P2 sat. Okay, well, 100 kilopascals is equal to 1 bar, so this should be 4.63 bar. Okay, and this is 1.324 bar. Okay, so my pressure at 7 bar is greater than either pure component saturation pressure, and so it should be I have a liquid and not a vapor. Okay, so we could tackle this a couple different ways. One would be to make this 0.7 bars, at which point it'd be a vapor, or we could go about this in all different sorts of ways. Okay, so how I'm going to solve it is I'm going to take this to be 0.7 bars, right? I'm assuming they just have a typo that's off by a factor of 10. Okay. All right. So by Y1 here, right, that's the composition of my mixture. It's just I'm a vapor, okay, and I'm going to increase the pressure until I become all liquid. And what I want to know is what pressure does the system fully become a liquid, and then what's the composition of that last bubble that condenses. Okay, and so anyways, so I'm going to start by I'm going to sketch a phase diagram. The phase diagram I'm going to sketch is we're at 110 degrees C, and we're going to change the pressure holding temperature constant. So I'm thinking in terms of a PXY phase diagram. So if I sketch my PXY, okay, with respect to the most volatile component, and acetone is the most volatile component, right? So P1 sat's greater than P2 sat. Okay, so I've got P1 sat here. My bubble line is going to be straight line for a system that obeys Raoult's law. Here's P2 sat, and here's my dew line. Okay, cool. Now, in this problem, all right, we're told that we have a mixture composition of Z1 is equal to 0.7, okay, and it's at a pressure, I'm going to take it to be 0.7 bars, which is down here in my vapor phase. Remember, low pressure is vapor, up here it's liquid, and in between it's two-phase. Okay, so my system, right, it's somewhere on this vertical line. Okay, so I'm starting as a vapor, and I'm going to increase the pressure, okay, until I become all liquid, right? And so where do I become all liquid? Well, if I start to increase the pressure where I hit my dew line, this corresponds to my dew pressure, or my dew point of the mixture. And so at my dew point, right, that's where my first liquid drop condenses. Okay, and my dew point, what's unique is that I have Y1, right? I read Y's for my dew line. Y1 is equal to Z1, and that's going to correspond to essentially my smallest x that I could obtain. But that's going to be, the limit in which my first liquid drop condenses. And then if I continue to increase the pressure, right, so I've got two phase. Now, once I hit my bubble point of that mixture, okay, so at my bubble point, I have that x1 is equal to z1, right? I read liquid compositions for my bubble line. So x1 is equal to z1, okay, and I have all liquid, okay. Cool, right? And the significance of this is if I have a pressure less than my dew pressure, then I'm down here in my vapor phase. if I have a pressure greater than my bubble point pressure, right, then I'm a liquid, I'm up here. And if I'm in between, I have a two-phase mixture. Okay, so at what pressure does a system fully become liquid? Well, at my bubble point is where I transition from two-phase to liquid, right? And all pressure is greater than my bubble point pressure, I'm going to have a liquid. Okay, cool. So I'm going to interpret problem A then, assuming I start at a pressure of 0.7 bars, right? I'm assuming I'm over here in the vapor. So I'm going to take this to be, what's my bubble point pressure, right? At what pressure does a system fully become liquid? Okay, and then at that pressure, what is the composition of my vapor bubble? Okay, cool. That's how I'm going to interpret it. What I want to do first is to go above and beyond. I want to calculate my dew pressure here and my bubble pressure here, right? Just to confirm, right, that that this pressure, right, to reassure myself that I'm in my liquid phase, and just for completeness, right, in terms of identifying where we are on our phase diagram. Okay, so all right, at what pressure does the system fully become liquid? That's become my bubble point pressure. Okay, and so how we get that is, well, what's key is that my bubble point, I have that my liquid composition is just equal to the composition of my mixture. Okay, and at my bubble point, I have two-phase coexistence. Okay, so in terms of doing a bubble P calculation, okay, the idea is well, I have a system at two-phase coexistence, so I can write down my isophilic acid equation, right? And we're told that our system can obey, assume it obeys Raoult's law. So vapor phase is an ideal gas, liquid phase is ideal. So Y1P is equal to X1 times P1 sat, and Y2P is equal to X2 times P2 sat. Okay, so remember, Raoult's law is just my isophagacity expression. It's my equilibrium relationships, only we're assuming our liquid phase is ideal, and vapor phases can be treated as an ideal gas. Okay, and Poynting correction is negligible. Okay, but as long as I'm at low pressure, assuming vapor phase is an ideal gas and Poynting correction is negligible, should be good. And as long as I have chemically similar compounds, assuming an ideal solution is good and reasonable as well. All right, so now in a bubble P calculation, okay, the key is well, at my bubble point, X1 is equal to Z1. So if I know the composition of my mixture, well, then I know my X1s. Okay. Now, here, right, we're told the temperature is 110 degrees C. So when I specify temperatures, when I think about a PXY, remember temperature is fixed. Okay. And when I look at my isophilic equations, key is, remember, P1 sat and P2 sat. This is pure component saturation pressure, pure component 1 and pure component 2. Remember, P1 sat and P2 sat, pure component saturation pressure, those are only a function of T. So think about Raoult's law, or not Raoult's law, Antoine's equation. All right, my vapor pressure is only a function of T. So specifying T is equivalent to fixing or specifying the value of P1 sat and P2 sat. Okay. On the left-hand side, right, P, right, that's what I want to calculate. I want to calculate my bubble point pressure. Okay, Y I don't know, right? I don't know, right, this Y value. Okay, so in a bubble P calculation, the idea, the strategy is, I'm going to take these two equations and I'm going to add them together. And by adding them together, I'm going to kill Y, right, and I'm going to isolate P, the quantity I'm trying to solve for. Okay, so the idea is if I add these two equations together, okay, on the left-hand side I have Y1P plus Y2P. Okay, that P is the same, so it becomes factored out. It's P times Y1 plus Y2. Y1 plus Y2, my mole fractions need to sum to 1. All right, so that's just P. Okay, so I'm left with, on the left-hand side, P is equal to X1 times P1 sat plus X2 times P2 sat. Okay, and to make this complete, as if I'm looking at my bubble point, I'm going to call P bubs. Then my X's, okay, my liquid compositions are just the compositions of my mixture. So that's going to be Z1 times P1 sat plus Z2 times P2 sat. Okay, we call this a bubble P calculation. Now, also as an aside, when we've sketched phase diagrams for PXY phase diagrams for ideal systems, right, my bubble line takes the form of a straight line between P2 sat and P1 sat. All right, here you go. Why? Because the bubble point pressure of my mixture is just the molar average of my pure component saturation pressures. Okay, so my bubble line is going to take the form of a straight line for my system that obeys Raoult's law. All right, cool. So that's how I'll calculate P bubs. Okay, and so we'll go over to MATLAB and we'll calculate P bubs here in a second. Let me just make a mark for it. Okay. Now, what I also want to calculate just for completeness is let's calculate P do, right? And the significance is that if my pressure is greater than P bubs, then I have a liquid. Okay, if my pressure is less than P do, I have a vapor, and if I'm in between, I have two phase. So knowledge of P bubs, P do are important because they're going to help me identify where I am on my phase diagram and identify what phase I have. Now, to form a dew point calculation, okay, so we'll call this a dew P. Okay, the other one was a bubble P, so let's call this a dew P calculation. Okay, the key is at my dew point. Okay, same thing. I have two phases at coexistence. Only now I know y1 is equal to z1. Right, it's equal to the composition of my mixture. So now I write my isostochastic equations down. Okay, for my system that obeys Raoult's law, y1p is equal to x1 times p1 sat. y2p is equal to x2 times p2 sat. Okay, so temperature is specified, right? That's the same as specifying p1 sat and p2 sat. Okay, and now I'm at my dew point, so y1 and y2 are equal to z1 and z2, so I know y1 and y2. Okay, p is what I want to solve for. x1 and x2, well, those are unknown, right? I don't know what they are. So how I'm going to get x1 and x2 is, well, I'm going to do the same trick where I sum these two equations and I'm going to kill them by the fact that x1 plus x2 is equal to 1. Right, so how we do that is I divide through by p1 sat and p2 sat. So this is going to become y1 p divided by p1 sat is equal to x1, and y2p divided by p2 sat is equal to x2. If I add those together, I'm going to bring it over here. Okay, again, p is the same in these two lines. So if I factor it out, I have p times y1 over p1 sat plus y2 over p2 sat, okay, is equal to x1 plus x2, which is equal to 1. So solving for p, okay, p is going to be equal to, okay, the inverse of this, y1 over p1 sat plus y2 over p2 sat raised to the power of 1. And to make it completeness, or make it complete, if I'm trying to calculate my dew pressure, well, at my dew point, y1 is equal to z1, and y2, well, that's equal to z2. Okay, cool. So I'm going to go over to MATLAB, and I want to calculate the two of those. Okay, so I can get those reference points and see where I am. Okay, all right, so for problem 1, okay, and again, in the problem, they call that y1, but I'm taking this as they have a vapor phase that they're going to try and condense, so they're just using y for the vapor phase. But to be consistent with the notation we've used throughout this course, right, that's my mixture composition, I'm going to take it to be z1. Okay, so z1 is equal to 0.7. z2 is going to be equal to 1 minus z1, right, it's my 0.3. P1 sat and P2 sat, I'm going to put them in bars because we're given a pressure here in bars. Okay, although I could use pascals. So I just remember 1 atm is 1.01325 times 10 to the 5 pascals, or 101.325 kilopascals, right? And so 1 bar is just 100 kilopascals. Okay, so P1 sat, right, 1 bar is approximately 1 atm. It's 1.01325 atms. So P1 sats, 4.63 bar. Okay, P2 sat. Right, and again, right, we're assuming Raoult's law, and that's because the problem's telling us to assume Raoult's law. Okay, P2 sat is 1.324 bars. Okay, so P bubs, okay, was equal to Z1 times P1 sat plus Z2 times P2 sat, and P dew, well, that was equal to Z1 divided by P1 sat plus Z2 divided by P2 sat, all that raised to power of -1. screen from the last problem. So running. So P bubs is 3.6382. Okay, and P do is 2.6471. Okay, so this point here, so P do, this is 2.6471. Okay, and this, my bubble point, well, that is at 3.6382. Okay, bars. Okay, so this is where in the problem statement they said pressure was 7 bars, which would put you up here. It would already be a liquid. And so that's where I'm assuming that maybe they meant something like, 1.7 or 0.7 bars. Just any pressure less than my dew pressure, they would put me here in my vapor phase, right? So then it makes sense that I'm down here in my vapor phase, and I want to increase the pressure till I hit my bubble point pressure, at which point, for that pressure and all pressures beyond, I am fully liquid. Okay. Cool. So I've got my bubble point pressure, my dew point pressure. So in terms of what pressure does a system fully become liquid, well, that's my bubble point pressure. That's my 3.6382, right? So that's my bubble point pressure, which I just computed. And then B, it says calculate the last bubble that condenses. Okay, what I'm going to interpret that is at my bubble point, that's when my system transitions from two-phase to liquid. And so the last bubble that would condense, well, that would be this vapor, right? The vapor, the vapor of the composition of the vapor phase at my bubble point, right? So it'd be solve for y1 at my bubble point. Okay. So if I were to do that, okay, how we would do it, okay, so if I go back to my P bubs calculation, is once I have my bubble point pressure, well, then I could just go up to either one of my isophigasity equations and solve for y1. Okay, so when I do that, okay, so I have y1p is equal to x1 times p1 sat. Okay, and for completeness then, we have y1 times p bub is equal to z1 times p1 sat. Okay, so to solve for y1 is equal to z1 times p1 sat, okay, divided by p bubs, okay, which is equal to z1 times p1 sat. Okay, and I have z, but you could also write x because x and z are the same at my bubble point. Okay, z1 times p1 sat plus z2 times p2 sat. Right. All right. So my comment is I have z's here. You could also write it as x, since at my bubble point my z's and x's are the same. Okay, so solving, so y, okay, well that's going to be equal to z1 times p1 sat divided by, and I'll just do p bubs here since we've computed it. Okay, so y is equal to 0.8909. Okay, and remember, right, this is my y max, right? So, hey, make sense of why y is so big. So y1 is equal to 0.8908. Okay, cool. That's good. All right. Then the last part is what is the fugacity of nitromethane, that's component 2, in the liquid when the system is at the conditions of part A. Okay. So for C, so at my bubble point, we're asked to calculate the fugacity of component 2 in the liquid phase. All right, well the key is going to be, the fugacity of component 2 in the liquid phase is at my bubble point I have vapor-liquid coexistence, right? So the fugacity of component 2 in the liquid, well that's going to be equal to the fugacity of component 2 in the vapor. Okay, how am I going to calculate it? Well, choose, right? So it should be then, remember we're assuming our system obeys Raoult's law, so the fugacity of component 2 in the liquid, Well, we're assuming that that's equal to x2 times p2 sat, okay, which in this case would be x2 is equal to z2 times p2 sat. And the vapor, right, vapor phase we're assuming to be an ideal gas, right, we're assuming our system's described by Raoult's law, so this would be y2 times p. Okay, so take your choice. Let's try both of them, right? It says calculate the fugacity of nitromethane in the liquid. Okay, so let's do both, right, and show that they're the same. Okay, so let's do F2L1, right? So temp 1. Okay, so we just calculated. So this is y1. Okay, so it would be equal to 1 minus y1. And actually, let me do this. So I know y2 is equal to 1 minus y1. Okay, so it's going to be equal to y2 times p, where p is p bubs. Okay, and so I should say here at my bubble point, right, y2p, right, this is p bubs. Right, I'm at my bubble point. Okay, so I did y2 times p, calculate fugacity 2 of my vapor phase, which should be equal to fugacity of 2 of my liquid. Okay. And then likewise, I should be able to compute this as F2L, right? And this is going to be, method number 2 would be x2, which is equal to z2 times p2 sat. So running, right, in both methods, all right, I get a fugacity of 0.3972. Okay, so both methods are consistent and give me the same value of 0.3972. Okay, so I end up with the fugacity of component 2 in the liquid is equal to 0.3972. Okay, cool. And that is in units of bar. And if you wanted to, you could have fun. You could calculate fugacity coefficients of, each component in the liquid and vapor phase. You could calculate fugacity of component 1. Right, but the problem's not asked for it, so I won't do it here. Okay, so hopefully that helps. Again, the one change I made is when I see this y here, right, I took that to be, Z1 composition of my mixture, and then the pressure 7 bars, right? I think the pressure should actually be, we want the pressure to be less than our due pressure, so it's a vapor. So I just said, hey, maybe it's a typo and it's 0.7 bars. But hopefully that helps. If you have any questions, by all means, let me know. I'll make sure I get the MATLAB code up with my solutions online.